over Voltaic cells, how it works, and calculate some cell potential. I hope you'll give it a try. You can find the worksheet on my website, and just going over it, if you go to my website and there's a link in the description, you'll see my website. You can pick the Electrochem section. In the Electrochem section, anything highlighted in yellow has a worksheet, so you just have to scroll down a little bit and you will be able to find it. Click on it and you'll find the worksheet that you can try. So the first part of the worksheet, and it is a quick worksheet going over the major concepts of Voltaic cell. And a lot of times you'll have a question that asks you to describe how the cell works. So in this one, we have the cell. It does tell us that zinc is on the left-hand side, copper is on the right. It also shows us that the electrons are moving from the zinc anode towards the copper cathode. But if we weren't sure which way the electrons were moving, we would just have to check page 7 of our data booklet, and we would see that our strongest OA, right, the one you see up here, undergoes a reduction, and that happens at your cathode. So copper has to be the cathode, and cathodes are known to be positive. And then your strongest RA is what you find on the bottom right, and that is what undergoes reduction, and that undergoes oxidation, and that happens at your anode. So our zinc electrode is our anode, and those are known to be negative. So that's our first bit. Number one, just if we are filling it in, it is just showing you your electron flow. And no matter what, your electrons flow from your anode over to the cathode. So you do want to decipher which one you have first before you fill in everything else. Then just going over a few more things, your salt bridge is what connects the two cells together. And that will have a salt solution. And within the salt solution, we'll always have cations flowing towards cathode and anions flowing towards the anode. And then down here in number 3, I'm just going to say we have the zinc ions floating in solution, and then that is coming from your zinc solution. I don't feel like this is really being specific of what it wanted us to show, so I'm just going to fill this in for this worksheet. And then this would be copper sulfate. And then this was just extra. I think it was supposed to point to the salt bridge, just with formatting it moved. So that's our first part, just understanding the way we're moving. And now what we want to remember is if this zinc is undergoing oxidation, it is essentially this reaction backwards. It is breaking up into zinc ions and electrons. So your ions, when it breaks apart, will be in solution, and your electrons are going to leave and go over to the cathode. So because of this breaking apart of that solid, this is going to decrease in mass because it's going to lose its ions to the solution and the electrons go over to the cathode. On the other hand, your copper 2 positive that is hanging out in the solution is going to join with those electrons, right? And when they come together, they make copper solid, and we're going to add more solid onto this cathode. And when you do that, that's going to increase in mass. Now, the other part that just completes the circuit, as the zinc 2 positive gets added to the solution, you're going to have a more positive charge in this beaker. So from your salt bridge, it is going to attract negative anions to neutralize those charges. Then from over here, those copper 2 positive, when they leave the solution, right, it's going to leave behind that sulfate ion, which is negative. So those positive ions from the salt bridge are going to come over to neutralize this beaker. So that's how the whole Voltaic cell works every single time, as long as you know which one is your anode and which one is your cathode. Now, if we write down a few more things, which we've just talked about, the reaction that's happening at the anode is your zinc solid breaks apart into zinc ions, which go into solution, right, because they're aqueous, and electrons. So just to balance out our charges, you would need 2. At the cathode, you have those copper ions in the solution gaining 2 electrons to make copper solid, and that's why we're adding mass to that electrode. Now, because of our electrons already being balanced, we can add these 2 half reactions together. If our electrons weren't balanced, we'd have to do that first before we can add it. And once we have that, we can see our full reaction of what's happening within the cell. And then going to the next one, D. In what directions do the electrons flow? They always flow from your anode to your cathode. So what's showing here is coming from your anode, going over to your cathode. And then in what direction do the cations from the salt bridge move? Well, we talked about that as well. As these copper 2 positive leave solution, it's going to leave behind a negative charge. So the positive ions from the salt bridge will go into the solution to neutralize. So they move towards the cathode. And this will always be the case. The positive ions from the bridge go towards the cathode. And then which way do the anions move? For the same reason, except opposite. When that zinc breaks apart, adding in those positive charges, the negative anions will come from the bridge to neutralize it. And it doesn't matter what our cell is, they always move towards the anode, those anions. Okay. So that's the first part, just knowing how our cell works. The second part is calculating cell potential. Here is a chart quickly here, but if you do take a look at your data booklet on page 7, this chart is not arranged in order, and you can tell based on those cell potentials. If you're looking at page 7, you have the most positive up top, and then it goes to the most negative, and that's how we have to arrange it. So when we're doing this and you're taking a look at cell potential, we have to remember that the E of the cell, so the total cell potential, is the cell potential at the cathode, and then you subtract the cell potential at the anode. And then just going over a few more things, we know the cathode is the site of reduction, and that's going to be your strongest OA. So your strongest OA will be the most positive when you're looking at the chart. If you're looking at your anode, it undergoes oxidation, and that means you're a reducing agent. So you are looking for what's most negative when you're filling this in. And then you're just plugging it in. So for instance, that first one, my zinc half cell and my copper half cell, I know already because we did this in the problem, but the zinc is at your anode and then the copper is at your cathode. So this part here is your anode and then this part is your cathode. So to calculate this, we're just grabbing those values. We would do 0.34 minus negative 0.76. Don't change any sign. This negative that's in the formula will allow us to flip it, turning it into oxidation. And then we plug that in and you'll see your total voltage is 1.10. And if we're looking for more practice doing the same thing, if you have iron reacting with copper, iron is more negative, so that would be your anode. Copper would be your cathode. So you would take that copper value, 0.34, and subtract negative 0.44, getting a total of 0.78. And we can keep going. Zinc as a half cell with silver. Silver is more positive. That will be your cathode. And zinc will be your anode. So just those values, 8.80 minus 0.76, you get 1.56. And then the last one with iron and silver. Iron is going to be your anode, silver is your cathode. So 0.80 minus negative 0.44 give 1.24. So I like cell potential questions because I find them easy as long as you can identify your anode and cathode and you know your formula. Now the last few questions we have here are just going through some theory. So what is the purpose of the salt bridge? If you don't have the salt bridge, you would have no voltage. So the salt bridge completes the circuit. So completes the circuit. That's a T. Is it coming there? Nope. Okay, this is just not wanting to write it down. That's okay. And it also keeps the cell from building up charges. So it keeps your half cells, from building up a charge. So as we saw, if there was not a salt bridge, right, our anode would build up a positive charge and your cathode would build up a negative charge. So keeps cells from building up charges. Keeps it neutral, in other words. So what happens to the mass of the anode? So as we talked about, at the anode, because it's going to split off into ions and electrons, it is decreasing. So it is decreasing in mass, and that is because it's undergoing oxidation. It's losing electrons, which means it's breaking up into its ion as well, and ions go into solution. And the other one, what is happening at the cathode? Well, that cathode is increasing in mass, and the reason why, it's undergoing reduction. So the ions within solution, that is what's undergoing reduction. It's going to gain electrons and make a solid, and then that solid is going to attach itself to the cathode. So that's our quick little worksheet going over how the voltaic cell works and how we calculate cell potential. I hope you found this helpful. If you did, please subscribe and look out for more worksheets and other activities that you can try and practice on my website. The link is in the description. Thanks for watching.